Alright, in this video we're going to be reviewing some vocabulary. There's a lot of terms that we expect you to be familiar with and to understand, and I've put a list here to kind of help me guide through this video. I'm guessing it's going to be fairly lengthy, so if there are some of these that you feel like you really know what that term is, feel free to skip around within the video and find the ones that you think you might want a refresher on or that you're not familiar with and want to understand. So I'm going to try to follow this order as much as possible and kind of mark them off as we go. That way, when you skip ahead, you can find the spot that you want to be in. Since I can't keep this on screen, I'm going to have my little note here that has this list, and I'll mark them off of there as we move forward. So starting out, our first term that we want to know is constant. So a constant is a number that doesn't change. So basically, you could think of it as a known number. So 4 is a constant, or 8, or 3.172, or pi. Anything that always has the same value is a constant. So if we use the word in terms of English, saying something is constant means that it doesn't change and it's always present. So that's a constant as opposed to a variable. A variable is a unknown number. It's a placeholder for some number whose value we don't know. We typically use letters like A or X or N. We also sometimes use other symbols that aren't letters or that are letters in different languages. So we use things like theta or alpha or other things like that. So those are placeholders. And interestingly, these Greek letters, theta, alpha, and other ones that we use, can stand in as variables, whereas pi, which is also a Greek letter, is a constant and always has the value of 3.141 and then on forever. So yeah, those are variables. Said I would mark these off as we go. So we did constant, we did variable. So constants and variables are two kinds of numbers. One, we know how much it is, and the other, we don't. Term is the next one. So a term is kind of like, I think of it as a mathematical unit. And that could be anything that's connected by only multiplication. So let's put connected by multiplication. So as examples, we could have something like 4. 4 is a term. It is also a constant. So a constant by itself is a term as far as that vocabulary is concerned. X is also a term. That's a variable. But we could combine some constants and variables by multiplying. So for example, 4x is also a term. So all of these are terms, and 4x, since it's a constant times a variable, is also a term. I don't really want to put term there because that makes it look like the others weren't terms. We can even have multiple variables. So if I had 3xy squared, that is also a term because everything here is connected by multiplication. Remember that this 4x is 4 times x, and this is 3 times, don't want that symbol, 3 times x times y is what 3xy squared means. So all of those things are connected by multiplying, so it's still a single term. All right. Along with term, we'll go ahead and do coefficient too. So a coefficient is it's kind of like the constant part of a term. So it's how many of a thing you have, how many there are. So for example, if we had 4x, which we know is a term from the previous one, we call this part the coefficient. So think of it as if this term has a size of x. That's how big it is, and it's 4 times that much. So if I think of those as separate x's, it's like x plus x plus x plus x. The things are x big, and there are 4 of them. So it's how many there are. Even in the case like 3xy squared, that would be xy squared, xy squared, xy squared. So again, I have 3 of those. So the 3 is the coefficient. So you'll also cover that in science this year as well, so you'll get familiar with that term if you're not already. So coefficient is just how many of a thing you have. I could also have something like 4 pi. The thing is pi big, and it's 4 times that. It's 4 of those things that are pi sized. All right, so term and coefficient, we're done with those. Let me get that. Okay, next, like terms. So we talked about what a term is and what it's made up of. It's often made up of a coefficient and some variables, or even a coefficient and constant, like we just saw with 4 pi. In that case, this is a coefficient, but it's not a variable that it's multiplied by, it's a constant. So it doesn't matter if we're multiplying together variables or constants, it still creates a term when we put it all together. So we have something called like terms. So like terms have the same size. So we said that the term was made up of how many there are and how big they are. So if I had 2x plus 3y, those are not like terms because this is 2 things that are x big, and this is 3 things that are y big. They're different sizes. But if I had 2x plus 3x, then those are like terms because it's 2 things that are x big, that's x plus x, and 3 things that are x big, x plus x plus x. And if I bring down this plus in the middle, then all of those are the same. They're all x's, so this is the same as 5x. So like terms have the same size, which by that we mean the same variables, or constants in the case of pi. And it allows us to add the coefficients together. So we can combine the coefficients and create a single term instead of 2 separate terms. Okay, so that's like terms. Next thing is operations or operators. So an operation is a thing that we do to things in math, how we change things. So we just used one. Our basic operators are plus, minus, times, and divide. There are lots of other operations in math that you can do, like square rooting, squaring, and other things that you haven't learned about yet. So any operation is basically changing or doing something to a term to change it. So in the case of 2x plus 3x, the operation that we're doing is to add them. So this symbol means add, as I'm sure you're familiar with. And there's some vocabulary that goes with each of these. So plus is addition, and the result of addition, so adding terms, is called, so this is the operation, this is the name, and this is the result. So when we add things, what we get is called a sum. So sum is the result of an addition operation. So in this problem here, we add 2x and 3x, and 5x is the sum of those 2 terms. Okay, so that's our heading. Next we have minus. Minus sign is called subtraction. Subtraction is fake, it doesn't really exist, and we call the result a difference. So the reason I say subtraction doesn't exist is because it's really just adding a negative number. So when we look at these two, they're basically two sides of the same coin. And you can always frame subtraction as adding a negative. So if I had 4 minus 3, then that's the exact same thing as 4 plus negative 3. So you're still really adding, you're just adding a negative number. But we refer to it as subtraction because it kind of is easier to think about that way a lot of times. Instead of putting plus a negative, we just put this 4 minus 3, and that makes sense that it's reversing what we do in addition. Times is multiplication. Multiplication. And we call the result of multiplication a product. And we saw that already when we had something like 4 times x, then we end up with a product of 4x. Likewise, you can multiply constants and have something like 2 times 3.4 and end up with 6.8. So you multiply two terms together and you get a product of them. And then division, just like subtraction, is kind of a fake operation because it's just multiplying by a fraction. So division, we end up with something called a quotient, and sometimes we end up with what's called a remainder. There's some leftover part. So a quotient, technically the remainder is part of the quotient, but something may divide evenly, and then it only has a quotient, like a whole number quotient, or it could have a remainder, in which case your quotient has a fraction in it. Okay, so those are our 4 basic operations and all of the vocabulary that goes with those. So let's knock all of them out together. Next thing we're going to look at is the term expression. So now we're getting into ones that you've probably seen but may not have used a lot that are super important for algebra. So an expression is kind of like a math statement of one or more terms. So going back to earlier examples, 4 would be a term, but I guess you could also call it an expression. It's just 4. Typically, when we talk about expressions, there's going to be some kind of adding and subtracting operations happening. So something like 4 plus 3x is we would call an expression because it is basically irreducible. We can't do anything to it to simplify it, and it's just going to be like that, and there's a plus in the middle. So if we are left with pluses or minuses, then rather than having a single term, we end up with an expression. That can be very simple or very complicated. So 3x minus 4xy plus 7q minus 31. That's still an expression because it's just a bunch of terms with pluses and minuses. So let's say a math statement of one or more terms separated by operators. In this case, pluses and minuses. Okay, so I think that kind of covers expression. We'll mention it more further down because it's really important. So I'm going to bold that one and then strike it out. Simplify. So expressions, so simplify means to combine terms in an expression. And that shows up several different ways. So a very simple one, like we've looked at above, is if I had 4x plus 2x, then I could simplify that. I'm not going to write an equal sign here because a really important thing about an expression is it's not an equation. It's just some things like 4x plus 2x. If I simplify that, so simplify, then I come up with 6x is an equivalent expression. So 4x plus 2x and 6x are equivalent. but the one on the right, 6x, is simplified, and the one on the left is not simplified. We also can do things like 3 times 2x minus 7. This is an expression, and it is considered not simplified. In fact, I'll add a word that's not review, so we're not going to be quizzing you on it right now, but this is called factored because there is something taken out of both of these terms, the 2x and the minus 7. In order to simplify it, we have to do something called distributing, which I know you're familiar with. We give this 3 to both of these numbers. So what happened on the left is the 3 had been taken away from both, and to simplify, we give it back and write this as 6x minus 21. And this would be the simplified form of the expression on the left. So basically, to be simplified, all like terms need to go together, and we need to get rid of all the parentheses. So we'll put without parentheses. I hadn't actually thought that through. That may not be 1,000,000% true, but generally you have to distribute anything. You can't leave things grouped in parentheses if you want it to be simplified. Okay, so simplify is usually the instructions that you're given when you have only an expression. So if you're given one of those like TikTok math puzzles or something that's like 4 times 2x minus 7 plus 2 times 3x minus 21, and it says to simplify that, or we say simplify it, then you can basically expand these or simplify these by multiplying them out and then put together the things that go together. So I could do 8x minus 28 by distributing this 4, and then I would need to multiply 2 times 3x is plus 6x, and then minus 21. And then I would combine whatever goes together. So simplifying can take multiple steps. It can happen, so we simplified somewhat here by distributing, and we can further simplify then by collecting our like terms or combining like terms. So as a final answer, I would get 14x minus 49. So importantly, in simplifying, we're not figuring out how big the variable is. It remains unknown even when we're finished. So this x is still unknown even at the end of our work. Okay, I think that covers simplify pretty well. Let's go to one that may be less familiar, which is evaluate. So evaluate is a big term in algebra and other higher maths. And it sounds new maybe, but you've probably used the term substitute or the really colloquial, not proper term of plug in. And that's really what evaluating is. So if I had an expression that says something like 4x minus 7, and I say x is equal to 2, then I can figure out what this expression is by substituting this 2 for x. So we plug it in or put it in place of the 2, and we call this evaluating this thing. So we're figuring out the actual value of this 4x minus 7 now becomes 4 times 2 minus 7. And that's equal to 8 minus 7, which is equal to 1. So now we do get an actual value for our expression by plugging in or substituting a value of x. And we then say we have evaluated this expression when x equals 2. And we'll do more with that, and evaluate, again, becomes pretty important. But you can think of basically simplify is an instruction you're given at the start of a problem. And your end result, so simplify, your result will be an expression. You may also be told as an instruction to evaluate expressions. So if you're told to evaluate, you end up with a number. So you get an actual answer for how much the expression was, rather than an expression with unknowns. And then finally, an instruction you could be given is solve. Solve, we'll talk about, I have it further down, but I'm going to mention it here because I already started this little thing. I'll get to it again when we get down there. So with solve, we end up with a value of the variable. We find out how much the variable was, whereas when we evaluated, we were told the amount of the variable going in. So that was given, whereas in solving, we figure out how much the variable is. So simplify, evaluate, and solve are some things that we get very confused in Algebra 1. Like really commonly, we confuse these three things, and they all mean importantly different things. So you simplify an expression or evaluate an expression if you're given a value of your variable, and you only solve things that have some kind of comparison of two expressions. So that's what we'll talk about next. I think within that, I maybe talked a little about order of operations, but not really. So when we're evaluating or simplifying expressions, we follow our order of operations. So order of operations, which we often abbreviate with the acronym PEMDAS, PEMDAS, stands for, remember, operations are like adding and subtracting and multiplying. It tells us what order to do operations if they occur kind of like side by side. So if I had something like 4x minus 2, remember that means 4 times x minus 2. Is this a good example? Maybe, I don't know. But if multiple things are happening to this x, so we're multiplying it by 4 and subtracting 2. So the multiplication operation has to happen first. I guess I can give an example here where order of operations is really important, which is with calculators. If I do something like negative 4 squared, then I have two operations happening here. There's a 4, and I'm doing two things to it. So it looks kind of like it's a negative 4, but really what I'm doing is saying I'm making the 4 negative, which is like multiplying it by negative 1, and I'm raising it to an exponent. So there's a multiplication operation and an exponent operation that are both trying to act on my 4 here. So if I follow the order of operations, it says the exponent happens first. So then I have negative times 4 squared. I'll put that in parentheses with it. Negative times 4 squared, which is negative 16. But usually, if we say square negative 4, what we mean is negative 4 as a quantity squared. So we use parentheses since they're the king of the operations, right? They're at the start of the list. They're the most important thing. It says you have to do what's in parentheses before anything else. So when things are unclear, we sometimes use parentheses to enforce an order of operations. So in this case, this means negative 4 times negative 4, which is going to give me a positive 16. And this is a thing that if you type this into a calculator, the top way, you get negative 16, and the bottom way, you get positive 16. Typically, we really mean this, so we can use parentheses in a calculator to make sure that we get the answer we actually need. So another place we can look at order of operations would be, say we did 3x minus x plus 7. So we have this minus that's trying to subtract this parentheses stuff. I guess this isn't necessarily it is order of operations, because I have 3x and I have x, but I can't combine those because they're trying to combine by subtraction. Subtraction in my list of operations is way, way back here at the end, adding and subtracting are together. They're the same like power level, but they're way at the back, whereas my parentheses, which is kind of in the way here, is way up in the front. So in order to work this out, I would have to follow the order of operations. First, I would try to do anything inside the parentheses. X plus 7 can't be simplified, so I'd leave that alone. But then this minus is a multiplication operation that is acting on this parentheses. So to get rid of that, we do what we looked at earlier, which is distributing it. We distribute it to these two terms, and then we have 3x minus 1x minus 7. With coefficients, I should have reminded us that here there's an invisible 1. So if we have a variable with no coefficient shown, then the coefficient is always 1. So 3x minus 1x is 2x minus 7. So notice that here we did multiplication and here we did subtraction. We followed in the order that PEMDAS told us to do. Yeah, I hope you're familiar with order of operations, and I didn't have really good examples for it, but I know you know what it is. But I guess if you've forgotten, we should define it. So the P is parentheses, the E is exponents, so that means like if we're squaring something or raising something to a power, we'll be doing quite a bit more with exponents this year than you've done before. And then MD go together. Remember that division is fake. So this is really just multiplication, but division goes with it because division is just multiplying by a fraction. And then finally we have addition, and the same way subtraction goes with it, even though subtraction is just addition. So those go together. Okay, let's move on from that and talk about comparing expressions. So I've titled this one Comparison, and there's a few things underneath this that I want to look at. So these are like comparisons of expressions. So this is going to relate to expressions. Examples, we have several kinds of ways to compare things. So if I say 4x is equal to 8, then this equal sign is a comparison. So we have different signs that we use to compare expressions. So I have an expression or a term 4x and an expression 8, and this equal sign says that they are the same size. Whereas if I put 4x and then this symbol and then 8, this symbol means greater than or bigger than. So that says 4x is more than 8, not equal to 8. If I put 4x is greater than or equal to 8 like that, then that means that the amount on the left is at least as big as the amount on the right. So 4x could be 8, but it can also be anything bigger than 8. So we call that one greater than or equal to. And then we have comparators that say something is smaller. So if I have 4x and that symbol and 8, that means less than. So 4x is less than 8. And finally, if I have this one, it says 4x is less than or equal to 8. So you should be familiar with those symbols, but they all have something in common. When we have these comparisons, which we call, well, let's define the things we've written here. So it said comparison. This thing, which is, we'll write it below. I want more room. Okay, so an equation and let's mark off comparison. All right, an equation is two equal is the key word, that's why it's called equation. You can see equal in there. Two equal expressions. So we use an equal sign between two expressions to say that they have the same value. Whereas in inequality is two expressions in which one is bigger or smaller. Where one, let's just say two expressions that may not be equal, because they still could be. We saw that above we had less than or equal and greater than or equal. So an inequality doesn't tell us that two things aren't equal, but it tells us they aren't always equal. So one could be bigger or smaller than the other. So an example of an equation like we put up there, 4x is equal to 8, and then an inequality, 4x is greater than 8. So depending on which comparison we're using, we have an equation or an inequality. But let's cross them out. Both of them have something in common, which is that we can be told to solve them. So solve, we mentioned briefly earlier. Solving means to isolate a variable to determine its value. And that last part is not always true. You don't always determine it in terms of a numeric value, but the idea is we get a variable by itself. So I'm sure when I wrote 4x equals 8, in your head you were already solving that and saying, in that case, x is equal to 2. So if 4x is equal to 8, x is equal to 2. And similarly, we can solve, equations or inequalities. And it works the exact same way. In fact, that's our first topic we'll really be working on for the first few days this year. So if I had 4x is greater than 8, then I also have x is greater than 2. And we solve them using the same tools. The tools that we use to isolate variables are called inverse operations. Remember that operations are like adding, subtracting, multiplying, and dividing. So we defined those earlier. And we defined an order of operations, which was PEMDAS. So our forward, when we're simplifying things, so if we are simplifying expressions or evaluating expressions, then we follow PEMDAS in a forward direction. However, if we're solving, so if we're trying to figure out what a variable is, then everything is backwards. So instead of following PEMDAS, we reverse it, and it would be SADMEP. So we follow this order whenever we're solving and use inverse operations. So inverse also is called opposite operations. So our inverse operations, if we have adding, I'll write it in words. So adding is opposite to subtracting. Multiplying is opposite to dividing. So next in our list after SADM is E. So exponents, I'm just going to put square here because we haven't really dealt with bigger exponents yet. So I'm going to put square. Yeah, I don't want to get into exponents right now. Okay, so squaring, hopefully, that the opposite is to do a square root. So if I take 2 and square it, I get 4. And then if I take the square root of 4, I get back to 2 again. So squaring and square rooting are opposite operations. That's not exactly what exponents go with here, but we're not ready for that yet. And then parentheses is kind of the opposite is distributing or factoring. And we'll talk a lot more about factoring later in the year, but that's basically saying that if I have 2 times x plus 4, then, and I distribute it, then I get 2x plus 8. Then if I take 2x plus 8 and I factor it, so I take out a greatest common factor from both terms, then I would divide both of them by 2 and get 2 times x plus 4. So distributing and factoring are opposites, but don't worry too much about that one till later on. We'll get a lot more familiar with factoring in second semester. Okay, I think that's enough on inverse operations, and hopefully you know about solving equations. If not, there are separate videos about how to actually go about solving equations. This video is more about just the vocabulary, not the solving and how to do the math. Okay, last thing, since we talked about inverse operations, I wanted to talk about 2 very important words for inverses. So the first one is an additive inverse, which sounds very fancy, but remember the inverse of adding is subtracting. So if I have the number 4, its additive inverse would just be -4. And what that means is when I combine them, I get 0. So whenever I combine something with its additive inverse, we get 0 as a result. So you could think of it as being a word that we use for additive inverse is opposite. So 4 and -4 are opposite numbers. One is positive, one is negative. We also just sometimes say it's the negative of that number, but opposite is a really commonly used one. I'd say opposite is most commonly used, more so than additive inverse even. Okay, so basically for any number, like say a is a number, its additive inverse is -a. And it doesn't matter if a was greater than or less than 0. So if I had the number -2, its additive inverse would be -2. And we know that that is +2. When we take a negative of a negative, it becomes positive. So the opposite of a positive is negative. The opposite of negative is positive. So if you ever see add inverse, remember the inverse operation of addition is just a minus or a subtraction. And they always add up to 0. The last thing we're going to define is not additive, multiplicative. So let me mark off additive inverse from our list, and we'll do the last one, which is multiplicative inverse. Multiplicative inverse. Again, that sounds like a big fancy word, but we see multiplication inverse. And we know that the opposite of, or the inverse of multiplying is dividing. So if I have the number 4, its multiplicative inverse is dividing by 4. So 4 and 1/4 are multiplicative inverses. Again, we don't typically use this word as often as a more common term that you've probably seen, which is reciprocal. So reciprocal means multiplicative inverse. And the important characteristic of additive inverse is they create what we call a 0 pair, or they add to 0. The multiplicative inverse, they multiply to make 1. So 4 times 1/4 is equal to 1. And it doesn't matter if a number is a nice integer number like 4 or is something like 2/3. If I have 2/3, its multiplicative inverse would be the flipped version of it, the reciprocal, which dividing by 2/3 would be 3/2. And you can see that when we multiply 2/3 times 3/2, we end up with 1, because 3 divided by 3 is 1, and 2 divided by 2 is 1, and 1 times 1 is 1. So reciprocal is an important thing. We use that at several points throughout the year, and remember that it's just the flipped version or the division version of whatever a number is. Yeah, I got to the end. I just realized I left a couple of things off of my list, so I'm going to add them now, even if you've already tuned out. Oh well. So the things that I wanted to cover aside from these were things that had to do with rational numbers. So I'll just put that here as our last topic and go through that to wrap up. So rational numbers. You may remember are part of what we call the real number system. So we have different categories of numbers that starts with the real numbers is like a big box. And then inside of that box, we have a smaller box called rational numbers. And then within that, we have an even smaller box called integers. And then we have whole numbers and we have natural numbers. So rational numbers are typically, or anything that can be expressed as a ratio. So the key part of that is the first 5 letters that says ratio. And that is anything that we can express as a fraction or as a repeating decimal or a terminating decimal. And there's some vocabulary with these that I want to make sure we cover, so that's why we're adding this at the end. So rational numbers include all of our regular numbers that we're used to seeing, like whole numbers or integers. So 4, -3, 75, those are all rational numbers, but they're also integers. So here I want to talk about the rational numbers that are not integers. So things like 3/4 or 1/3 or 2.718529, all of those are rational numbers. And that's because we can express them all as a ratio. As opposed to something like pi, which is irrational because pi goes on forever and we can't express it as a fraction. If you're confused as to how this one can be expressed as a fraction, just move the decimal over a bunch of places. So if I multiply this by 10, 100, 1,000, 10,000, 100,000, a million, then it's going to be, instead of a decimal, it would be 2718529, but we multiplied it by a million, so that's out of a million. So we can write any decimal that ends as a fraction just by scooting the decimal over, kind of like how any percent is a fraction. So if I write 37%, that's the same as 0.37, which is 37 out of 100. And out of is per, and 100 is cent, right? There's 100 cents in a dollar. So percent literally means out of 100, and we can write any terminating decimal out of some power of 10. Just it's going to get a lot more zeros behind it the more decimals we had. Okay, so vocabulary with rational numbers. Main thing I want us to remember is that in a fraction, the top part is called the numerator, and the bottom part is called the denominator. If we want fractions to be combined, then they need to have the same denominator. Again, the focus here is vocabulary, not math. So top number is numerator, bottom number is denominator. If we call something an improper fraction when the numerator is greater than the denominator. So something like 7/4 we call an improper fraction. There's nothing wrong about it, though. Improper sounds like it's not okay, but it's actually the best way to write that number in higher level math. You've probably also written them as what we call mixed numbers. Mixed numbers are written the same thing, numerator is bigger than denominator, but we take out as many whole numbers as we can. So this 7 over 4, we would rewrite and say, well, that's 4/4 plus 3/4. So that's 1 and 3/4, and we write it like that. So the problem with that is we have two operations going on there. So when we're trying to solve equations, which is a huge part of algebra and higher math, then what we're really dealing with isn't 1 and 3/4, it's 1 and 3/4. So there's both a plus sign and a division sign in this same term, in this same piece. And that they have different priorities in our order of operations. So having both a plus and a division makes it impossible to do our inverse operations and to solve equations that involve that mixed number. So generally when solving, we use improper fractions and not mixed numbers. Mixed numbers are okay as a final solution to something. So if I end up with x equals 31 over 12, maybe I don't like how that answer looks, and then I can convert that to 2 and 7/12 as a final answer. And that's okay, but it's unnecessary. We can just leave 31 over 12 as a final answer. But definitely don't use mixed numbers within a problem as you're working something out. They will cause everything to go wrong. Okay, I think that covers everything I wanted to do in this video, and we'll cross out our last thing as a reward. Great, so there's our vocab review.